this video, we'll be looking at the final part of the particles and quantum topic, wave-particle duality. Now, wave-particle duality is the most wild aspect of the specification. It's a very peculiar topic that requires a bit of thinking outside the box. Now, it does tie up some of what we've covered already, and some of what will be covered later in the waves topic. But let's look at the obvious things to start with. We know what particles are because of how particles work, what they do, such as collide and carry charge. These are basic properties of particles and therefore considered to be a particle nature. But we've seen this with light as well. Now, considering light as a wave is one thing, but we can treat light as a particle because it demonstrates a particle-like nature in the photoelectric effect. The very fact that a photon of light transfers all of its energy in a single interaction, that discrete amount of energy that it carries, is very similar to the mass that would be carried by a particle. So this is a particle nature of light. And we know that when a photon doesn't provide adequate energy, no electrons leave the surface. But if you exceed the work function, as shown here, then there's enough energy plus more to turn into kinetic energy. So this packet of energy concept is just like a particle. So we consider that to be a particle nature of a wave. But it does work both ways. We know something is a wave because it'll carry out simple interactions like diffraction. Diffraction is a defining feature of waves, something unique that they can do. So as a wave passes through a gap, it'll spread out. We know that if a particle went through a gap, it would just go straight through. That is, till we experimented with electrons. So it's possible to accelerate electrons through a magnetic field to do this same effect. And what's seen is that as a stream of electrons reaches this gap of an appropriate size, they will diffract. You will end up with an interference pattern being produced on a screen, as can be seen by the rings on this diagram. So this interference pattern, as you'll see in the waves topic, is a way of illustrating diffraction happening on a very small scale. So this is evidence of particles behaving like waves. So this is wave-particle duality, the very idea that particles can act like waves and that waves can act like particles, and it just depends on the situation. Now, Louis de Broglie came up with an equation to link this all together in a single relationship, and that is lambda equals h over p, or h over mv. So lambda in this case is not just a normal wavelength, it is considered to be the de Broglie wavelength. Now that means if we're dealing with a particle, this is the equivalent wavelength that it should have if it were a wave, or when it behaves like a wave. So we know in diffraction that the gap should match the wavelength of the wave for maximum diffraction. So we could find an equivalent gap size for a particle. Now this works for the electron in the example above. Sadly, the gap for anything bigger than an electron is too small for the particle to fit through. H is Planck's constant as usual, and P is the symbol for momentum in kilogram meters per second. Now, we're also shown momentum is given as mv, so mass times velocity. So very physical properties of particles. Now, secretly, this is the only place on the equation sheet that actually shows you the symbol P for momentum and that it is equal to mv, which is quite peculiar. It's also worth noting the fact that m and v are used here means that the kinetic energy equation can also pop up, so keep an eye out for that being linked in. And that's the end of this topic. Thank you for your time.